Okay, so today will be entirely taken up by the theorem at the end of lecture 11. But before we get into that, I need to maybe say a brief word about equivalence relations. These are things I've sort of said at various points, for example in the tutorials or in passing in the lectures. But since we're going to be using it in such a crucial way through this whole argument, and the argument is going to be, pretty involved. This is an hour at the coalface. Okay, so this is exercise L11.7. Okay, so I'm just going to be using this throughout the lecture. Well, maybe I won't write the whole thing, but just the essential content. So suppose I have a quotient map. So tilde is an equivalence relation on a topological space. Then there's a bijection between open subsets of x mod tilde, and let's call those U, say, with what I'm going to call saturated open subsets of x. And that's U maps to rho inverse U. So I'm going to call an open subset, let's say V of x, saturated. Now saturated is with respect to this equivalence relation. If whenever you have a pair which is in the equivalence relation and one element of the pair is in V, then the other element of the pair is also in V. Okay? It's clear that the inverse image of an open subset is saturated, and if you think about it, you'll see every saturated open subset is the inverse image of, well, its image under rho, in fact. Okay, secondly, I've sort of said out loud what the equivalence relation generated by a set of pairs is. So a relation is just a subset of a Cartesian product of a set with itself. Let's suppose it's non-empty. So the equivalence relation generated okay, well, maybe I'll just describe it. So R tilde is going to be the set of pairs E prime which informally speaking have the property that you can reach E prime from E using things in the relation or their reversals. Right? You can sort of think about things in R. I mean, a graph is kind of a relation-like object, right? You take the set of vertices and then some of them are connected by edges and some of them are not. So visualize E is the vertices of a graph and R is the edges. The fact that I'm looking at eventually something that's reflexive says it's unoriented. So imagine walking along the edges of the graph, which is specified by R, from vertex to vertex, and any two vertices which are connected, you want to put in R tilde. That's the idea. So we say a pair is in the relation if there exists a sequence E, E0, E1, ... En equals E prime. I'll say what n equals, so n equals 0, it's clear what that means. So if there's a sequence of such things in E, such that for each relevant index I, either the pair that appears in the list as consecutive elements is in the relation, or its reversal is in the relation. And we need that because we don't know ahead of time that R is symmetric. Okay, so the exercise says prove R tilde is, well, first of all, an equivalence relation. It's reflexive, transitive, and symmetric. And prove that any other equivalence relation which contains R, So an equivalence relation is a subset of E cross E, and prove that any other equivalence relation containing R contains R tilde. Right? So when I say the equivalence relation generated by a set of pairs, which is the way I've been defining equivalence relations, I just mean the intersection of all equivalence relations containing R, but there it is concretely. It's that R tilde. Okay? So this is pretty important for the rest of the lecture. So are we clear on that? Are there any questions? Okay. So in practice, maybe it's very difficult to describe in some concrete way what R tilde is, I mean, apart from that, right? But in the cases we're going to be looking at, say, that come up in dealing with CW complexes, you know, it's often, with just a little bit of work, you can figure out what all the things in R tilde are. And I need one definition before I get into the mess of the theorem. So a continuous map between topological spaces, well, the inverse image of open sets is open by definition. Such a thing is called open if it sends open sets to open sets. Well, for example, the homeomorphism is open, but there are other examples of open continuous maps that come up. All right, so theorem. A finite CW complex is Hausdorff. Okay, so remember what Hausdorff meant. Hausdorff meant that given any two distinct points, x and y in my space, there existed disjoint open neighborhoods of x and y respectively. Full stop, end of sentence. Yeah? Okay. So I want to prove that a finite CW complex is Hausdorff. Well, we proved that CW complexes, finite CW complexes, were compact. That was easy, right? Because disjoint unions of compact things were compact, quotients of compact things were compact. So, okay. CW complexes are constructed by disjoint unions and quotients, so they're compact, from compact pieces. Right? Well, quotients of Hausdorff things are not Hausdorff. We discussed that last time with the line with a double point. So this is not automatic. Yeah. Yeah, I didn't hear the word at the end, the interpretation of
like what you're actually doing with taking these
what I'm doing with taking the sequences. Yeah. Yeah, maybe the so let's consider for instance the set 1, 2, 3. And let's say R, okay, so R's got to be a set of pairs. So let's say 1, 2, 3, 2, and that's it. Okay, so that's not an equivalence relation, right? To be an equivalence relation, it would have to in particular be reflexive, which would mean that, so let's write n tilde m to just be an indication that the pair n comma m is in the relation. That's what we usually mean when we write a symbol for a relation. Okay, well, so let's maybe, well, we could put an R on it if we wanted to be very precise. Okay, so 1 is related to 2, but it's not the case that 2 is related to 1. Well, because the pair 2, 1 is not in the relation. So this is not an equivalence relation because it's not reflexive. Okay, so what would this is an instruction for how to write down R tilde. And to run the instruction, what I'm going to do is look at all the paths that it's sort of telling me about. So think of these as paths. Okay, so there's 1, there's 2, there's 3. Now, they're ordered pairs, so they have a direction. So let me indicate that with the green chalk and an arrow. So 1 and 2 is in there, and 3 and 2 is in there. 2 to 3 is not. Okay, so that's it. Those are the pairs that are present in R. All right, so to get to R tilde, which I'm going to draw in red. Okay, so this is R. And then I've got R tilde. Okay, so I'm going to draw a red arrow from E to E prime. If I can set up some sequence of green arrows, right? So to say that E0, so I need E0, E1 to be in there, or E1, E0 to be in there. Okay, so here's an example of a path. 1, 2, 3. That's a valid path of this kind because 1, 2 is in R, and for consecutive pairs to be valid consecutive pairs in the path, I just need either, well, in this case, 1, 2 to be in the relation, or 2, 1 to be in the relation. Well, 1, 2 is in there, so I'm fine. And, well, 2, 3 is not in the relation, but 3, 2 is. Okay, so therefore, 1, 2 is in R tilde. For that pair to be in R tilde, I just had to produce a single sequence with this property that all the consecutive pairs were either in R or their reversals were in R. Okay, so you can see here I just walked along this arrow in the correct direction and then backwards along this arrow, and so I'm allowed to put in the red arrow. Yes, thank you. Yes, very good. Yeah, but that brings up a relevant point, which is, well, everything in R is already in R tilde. That's the n equals 0 case, right? So if I took, well, that's the reflexive case, rather. So the n equals 1 case would be just a pair of elements of E, such that either that pair is in R or its reversal is in R. So the n equals 1 case is directly throwing in everything in R and all the reversals of everything in R. Okay, so I know that 1, 2 is in R, and 3, 2 is in R, and the reversal of everything in R is also in R. That's the n equals 1 case with the second part of the definition. Okay, so what about 3, 1? Well, if I know 1, 3 is in the relation, I just have to write down the same sequence backwards. And that'll work because my check for whether a sequence is in, which is allowed or not, is a path in the language I'm using. The check for whether a sequence of elements of E is a path is symmetric symmetric with respect to interchanging each sort of pair, right? Because I just need 3, 2, the pair, to be sort of good. And, well, 2, 3 was good, and being good, that is, either a pair or its reversal being in R, is clearly invariant under permutation. So, all right, so that's also in my relation. What about 1, 1? Well, 1, 1 is not in R, but that's the empty sequence. That's the n equals 0 case, right? In the n equals 0 case, there's no check because my indices, there's an empty set of indices. So any sort of just single step is already in there, so that's all these. Okay, have I got everything with red now? I think so. 1 to 3, 3 to 1, 1 to 2, 2 to 1, 2 to 3, 3 to 1. I think so. Okay, I mean, it's everything. Everything's related to everything else, right? So R tilde is 1, 1, 2, 2, 3, 3, 1, 2, 2, 1, 1, 3, 3, 1, 2, 3, 3, 2. I hope. Okay, so I think. Yeah, thanks for the question. I should have done that example at the beginning. Does that make it clearer? Yeah. Any other questions about this? All right. Okay. So, proof. Well, the proof of compactness was by induction on the construction, and this is the same. So a CW complex X, by hypothesis, comes along with, well, there exists a sequence of spaces x0, x1, dot, 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 xn minus 1, xn is x, with the property that x0 is finite and discrete. Well, discrete means every set is open. In particular, singletons are open. So if I have two distinct elements of x0, just take the singletons. They're open neighborhoods and they're disjoint. So x0 is trivially Hausdorff. And each xi for I greater than or equal to 1 is constructed from xi minus 1 by a push-out do I want to give that a name? Maybe not. Okay, so that is the disjoint union. Okay, so as before, this is just a copy of the I-1 sphere labeled by alpha. This index set is finite. It's part of the definition, or I can take it to be finite. It's part of the definition. The left-hand map is just the inclusion of the boundary of the I disk and F are the attaching maps. All right, so well, xi minus 1 is Hausdorff by the inductive hypothesis. And, well, the disk is closed and bounded as a subset of Ri, so it's also Hausdorff. Well, I don't know why I'm saying it like that. It's as if I'm justifying it's compact. So closed and bounded is not really relevant. It's a subspace of Ri, right? So therefore Hausdorff. A subspace of a Hausdorff space is Hausdorff. So it's a metric space. And a finite disjoint union of Hausdorff spaces. Well, any disjoint union of Hausdorff spaces is Hausdorff. So this thing there is Hausdorff. But as I mentioned at the beginning, quotients of Hausdorff spaces need not be Hausdorff, so we really need an argument here. We need to pay attention to what's actually happening. So let's now do that. All right, so let rho be the quotient map. Okay, so now what I want to do is actually describe explicitly what this relation tilde is. Okay, so if I take distinct, well, So if they're equal in the quotient, well then by definition the pair xy belongs to this equivalence relation. And that equivalence relation was defined in a certain way to be generated by pairs, recall? So it was generated by pairs that said for every point here, the image under F is equivalent to the image under that vertical map. That was a generating set of pairs for the equivalence relation, and part 2 here tells you what the equivalence relation generated thereby is. Okay, so by part 2 there must be a sequence beginning with X and ending with Y. And at each stage, either the pair as you see it in the ordering or the reversal has to be in the generating set of pairs. So that is to say, either EI plus 1 or EI plus 1 EI is in the set of pairs which look like FS, S, S in those circles. Right? That's the generating set of pairs. And maybe it's worth drawing the picture now. Didn't leave myself room for all the bits, did I? Okay, here goes. All right. So there's my circle. There's my disk. There's my attaching map. Well, you know, actually there's more than one circle. I'll just draw the case for this. I mean, potentially more than one circle. Let me just draw the case where there's one. So that's my xi minus 1. And then I've glued that disk into the space along that bounding circle. It's worth pointing out, as it'll be significant in a minute, it's not like I cut out that circle and there was a hole and then I filled it in, right? The point, the point inside, whatever that means, right? This is not necessarily actually something that looks like a sphere, but you're imagining some topological space. Whatever points are inside, not that that really means anything, but they're not taken away somehow, right? So they're still there. That's like a little adjoining room that's cut off by a wall in this picture, right? it could be like a sphere with that part taken out, so it's actually empty, and then I glue it back in, but it's not. That's not indicated by the picture. Okay, and that's xi. All right. So what are the kinds of pairs we're talking about? So SFS, well, there's S. There's FS. And there's, so this S here, it's in this disjoint union, but you're meant to read this as sitting inside the disk, right? So I have been writing iota previously for this map, and writing down explicitly iota, that's just going to be a mess in this case. So just identify that as a subset of the disk, which of course it is. And then there's S. And those 2 points, which both live in the disjoint union, are set equal by these generating pairs. Okay, and I guess they end up both being this point here. All right. Okay, so you can check that tilde is just the following set of pairs. Well, it's an equivalence relation, so it has to be reflexive. It contains the generating pairs and their reversals. Well, it's symmetric, so that has to be true. And then there's some sort of two-step consequences, right? Okay, and those are of the form x, y, where x, y, and both on the boundary of the disk, and they are sent to the same point by the attaching map. Okay, those pairs aren't literally in the generating set, but I get them in two steps because suppose I have 2 points here, say S and S prime, which go to the same point here. Well, that point by these pairs, this guy is the same as that guy is the same as that guy. So they have to be by transitivity in the relation, and that's it. So that's an equivalence relation, and it's the smallest one containing the generating set, so that's everything. Okay, so it's not so bad. Okay, so, well, what are we trying to do? We're trying to prove it's Hausdorff, right? So what we're going to say is take two distinct points in xi, and we're going to try and construct a pair of open neighborhoods which are disjoint, which contain them. Well, there's some easy cases. This is so annoying now. Yeah, okay. So I'm going to do it this way. I'm going to bring this down and work on that board because I want to keep messing with this picture, otherwise it's incomprehensible what's going on. Okay, so here are the easy cases. Well, take a pair of points, x and y, which is just far away from the action, so to speak. Right? So we started with xi minus 1 and some stuff got glued in. But if x and y are just miles away from where anything happened, well, there's no difficulty constructing open neighborhoods which are also disjoint from where everything happened because the place where everything happened was compact and therefore closed. Right? So that's the technical point. Well, why is the place, where everything happened compact and therefore closed? Well, because it's the image of a bunch of circles, and circles are compact. So. Right? So take all those circles and the attaching maps, send them to some subset of xi minus 1. The image of that attaching map is the union of all the images of the individual circles, and F is continuous, and this is compact, and the continuous image of a compact set is compact, so that is compact. Right? Well, but xi minus 1 was Hausdorff by the inductive hypothesis. Okay, so those little circles that are drawn in xi minus 1 actually are, as you would expect, a closed subspace of xi minus 1. All right, so I'm still in the business of making this point about the case where the pairs of points are far away from where the attaching happened. So what is the place where nothing got attached? Well, it's the complement of that within xi minus 1. So okay, so look at the inclusion of that open subset in xi minus 1. Then sit xi minus 1 inside the disjoint union, and then take the quotient map. So this is the right-hand vertical map in that diagram. So that map is injective. Well, how do I know it's injective from what's already on the board? I mean, in terms of the picture, it's sort of clear, right? What I'm saying is take 2 points which are away from the images of those circles and then look at them in the quotient. Well, how could they possibly get identified? So they can't be the same, therefore that map is injective. But in terms of what's on the board formally, what's the argument? Yeah, exactly. I've already written on the board exactly what gets identified by the quotient, right? That's it. There's not some implicit things here which we haven't named. We've named every single pair of points in, well, not just in xi minus 1, but in the disjoint union of xi minus 1 and di. We've named every single pair which gets sent to the same thing by rho, because rho is exactly the thing that sends an element to its equivalence class. Okay, so look at tilde. Do you see any pairs which look like x comma y, where x and y are in xi minus 1 and are not of the form f of s? No. Right? Well, okay, I actually just said a lie, right? I didn't say they were distinct, but okay, I think that was clear. So any distinct pair of points, which is in xi minus 1, well, these involve one of them being in the image of f, and these involve both of them being in the boundary circles. And they're talking about points over here, in fact, not about points coming from this part of the disjoint union. Okay, so from the way we've described tilde, okay, so we know that's injective. And it's open. Well, that's by the first part of that exercise. Yeah.
Sorry, just to be clear, so the map you're talking about there is just sending x to x, right?
Yeah, that's right. Yeah, yeah, it's just sending x to. It's the quotient map. Yeah, that's right. Well, strictly speaking, it's sitting xi minus 1. There's no harm in me just writing it out explicitly. So. Yeah, so xi minus 1 sits inside the disjoint union. And then there's the quotient map. Right, so think of this as just an inclusion, and then that sends an element to its equivalence class under tilde. Yep.
I'm sure I've already said this, but what does the curly arrow mean?
Oh, I probably haven't said that. Yeah, that's take this, stretch it out. That's all. It just means it's a subset of.
Okay, cool.
Yeah. Yeah, I guess it's typical notation, I guess, for more categorically minded people, but it's just because this looks gross, right? It's like a short stubby thing and a nice, beautiful arrow. So, okay. Other questions? All right. Why is it open? Well, that was the first part of the exercise, right? So remember, I said that open subsets of the quotient are in bijection with saturated open subsets of the space which is being quotiented. Okay, so if I want to show that so this is an open subset of xi minus 1, and therefore an open subset of the disjoint union. if I want to show its image is open, I just need to show that open subset is saturated. That's it. Okay, so is this open set saturated? Well, let's have a look at our picture. To be saturated, here's an open subset, U of xi minus 1. Right? Is it saturated? Well, to be saturated, I'd have to argue that if I have any 2 points with one of them, well, this one related to this one in the equivalence relation, and one of them in U, the other one is in U. Well, we've just been discussing that the only way for 2 points away from the image of all those circles to be in the equivalence relation is this. So they have to be equal. Okay, so clearly then an open subset of that complement, the complement of the image of all the circles, is saturated. Right, so that's why it's open. Okay, so I'm still making this argument that I started with about the easy cases. Right? Well, this basically settles the easy case where both the points are in xi minus 1 away from the boundary circles. And then we can do the same thing for the disks, basically. X. Okay, so by BI, maybe I should write all those. Right, the disk was less than or equal to, BI is less than. Okay, so there's some gluing business happening at the boundaries of the disks, but if I just take, I guess it's the green part here, if I just take the interior of any disk and then sit it inside the disjoint union and then map it to the quotient. Okay, so that ends up being this green part here. That map is injective, again look at tilde, and it's open, again look at tilde, by the same argument. The map on the whole disk is not injective because of this stuff here, right? Points on the boundary can get identified. But restricted to the interior, it's injective. All right, so that takes care of so maybe I'll draw it here. So imagine this is an open subset of the open part of the disk, BI. The image of that in the quotient is something that looks like that. And here, right, so that's some open part ended up as some open part. Okay, so here's the easy cases of the Hausdorff. Okay, so take points in the quotient, x and y, and suppose that they're either, they are not at the gluing site. That's all that says. Neither of them are at the site where something was glued. Which is to say, they're either out here, so they're in xi minus 1 and in the image of the open continuous injective map from 2, or they're in the part that was glued on, but not where it was actually glued. Yeah.
Does that include the bit of the disk that sort of closes off the room?
Yeah, oh, that's a good point, yeah.
So,
Yeah,
so the only parts we're not talking about is the boundary where it joins.
that's right, yeah. So this guy here is also fine.
Part of XI, yeah.
Yeah, that's right. Right, so the continuous maps in 2 and 3 is, so it's in the image of xi minus 1 away from the images of the disks, which includes that guy there, which lands there, or it's in the image of the BI alphas. I mean, there's more than one disk, right? So imagine some finite number of these things. So the image of one of these disks, the open part, which ends up being the stuff that's glued on, but away from the boundary, which has become glued in. Okay, so we're considering both points of that form, not necessarily coming from the same bit, right? So I could have this being my x and that being my y, or x and y could be coming from two different disks. Right? Okay, well, since the spaces involved are Hausdorff, the first, well, because it comes from a metric space, and the second, even I don't know what that's supposed to be. A J, I guess. I hope no. You threw me off with the whole J thing. Okay. So since BI and XI minus 1 are Hausdorff, okay, so the first, because it's a metric, comes from a metric space, and this one by inductive hypothesis, this part's done, right? Because, okay, I mean, let's say they have the configuration I've shown, and there's some other cases, but this is, sufficiently general to show you what's going on. Okay, this X here, choose a pre-image. It only has one, so I guess I didn't get to choose. Because it's in the image of this injective map and nothing outside that maps onto it, right? Okay, so choose a pre-image. Let's call the pre-image X0. We'll be doing that later. And choose a pre-image of this. Again, there's exactly one. It's in some disk. Let's call that Y0. Now, in this case, we'll just choose an open subset of the disk containing Y0 and not touching the boundary, and here choose an open subset of Xi minus 1 not touching the gluing sites. Well, they're closed, so I can do that. And then the images, well, that's why I said those maps were open, right? So the image, the map Xi minus 1 subtract the images of the circles. That's an open map, so it sends that open set to an open set here. It's saturated, as we've discussed. So that's an open neighborhood of X, and this, for the same reason, gives me an open neighborhood of Y. And by the way things are set up, they don't meet, so we're done. Now, the only tricky case where we'd actually have to use Hausdorffness would be if Y was here, say, and there, then Y0 would be there. But then Xi minus 1 is Hausdorff, so I can choose those that don't meet, and then they won't meet in the quotient either. And if they both lay in the image of a single open disk, then I would use that BI is Hausdorff to do the same. Okay, so I hope you're convinced. Disjoint open neighborhoods Xi. Okay, and the tricky cases we'll do next time. So we'll stop there. Sorry for running over time.